conduct within FLAME during the main cost predict assembly. But I want to highlight here that FLAME, and at least how I see FLAME, is not just a project, but it's more like a community that aspires to deliver the next generation projections for the global coastal ocean to help us understand the impacts of climate change in terms of physics, ecosystem, hazards, and services. So by now, we have a relatively good understanding of the impacts of climate change in the open ocean and at least on global scales. And this is because in recent years, there have been dedicated international initiatives that include collaboration amongst climate centers around the world, that they have defined very precise protocols that are used together with global climate models to deliver projections of the impacts of climate change in the Earth system on global scales and with focus in the open ocean. So such initiatives, for example, are the Couple Model Intercomparison Project and the Dedicated Ocean Model Intercomparison Project. However, the projections that come out from these initiatives, from these global climate models, cannot provide reliable information in coastal scales. In recent years, there has been some effort to project the impacts of climate change on coastal scales in very specific coastal regions, but this effort has been very fragmented. So if we are to address the impacts of climate change in the coastal ocean worldwide in a consistent manner, we need a dedicated global coastal ocean model intercomparison project. And that's the main aspiration and the most challenging aspiration of FLAME, to help the community establish this GCO MIP. Now, if we are, the first step towards establishing this GCO MIP is to establish the protocols that the projections delivered under this GCO MIP follow. And we have to do that in a meaningful way, such it will allow us intercomparison amongst these projections. So within this protocol, we have to set the technical guidelines for these projections, like, for example, what resolution the models that we're using for these projections should have, how we should treat the interactions among the different Earth system components, what downscaling methods we're using. But this protocol should also have guidelines about the outputs that we deliver, what set of variables we should be delivering and at what temporal frequency, and what format this data should be, and accompanied with what metadata. And this part of the protocol should be designed with the needs of the end users in mind. In addition, this protocol should include guidelines about what emission scenarios we should prioritize in, or if we should start focusing in very specific region. And also how we treat, we should disseminate how we treat the uncertainty within these projections that we deliver. And this part of the protocol should be designed with the stakeholders in mind. So if this protocol will be meaningful, if we are to make it meaningful, such that it will allow us to have an intercomparison among the projections that it delivers, it needs to be designed through a collaboration amongst the modeling practitioners, the people that they are using the outputs from this GCO MIP, either for research or for climate services, and also the stakeholders. And this is the main aim of the workshop today, to have people that have somewhat different background, different expertise, that come from somewhat different sectors, discussing and deciding on the first level priorities that this protocol should follow. And this is because once we have these first level priorities, then the secondary details and more technical aspects can be set out and drafted by a smaller group of practitioners and specialists to share back to the community for agreement. Now, in terms of the agenda, this morning there will be an introduction to climate downscaling by Jason Holt, follow my introduction, I guess. Then we're going to have presentations on 4 case studies. We'll have 2 breakout group discussions that they will be followed by a feedback discussion where we will all gather again together, and each group will have about 5 minutes to present highlights of what was discussed in the group. And I just want to highlight here that you will be switching themes among the breakout group session 1 and among the breakout group session 2. And you have provided your preferences about these themes, but we may have reassigned you to balance out the groups in terms of expertise. There are printed handouts on where you have been assigned. You will find them somewhere. And if you were late to give your preferences, then please just put your name somewhere in one theme. You're not children. I mean, you can go wherever you want in the end. Maybe, but please try to follow what we set out. Just to remind you, the main themes of the breakout discussions, it's climate ocean dynamical downscaling, coastal estuarine and urban downscaling, biogeochemistry and ecosystem modeling, and user perspective. There will be 2 coffee breaks and lunch that will all be provided, and then we will conclude the workshop with an open discussion in the evening. Just to mention here that during the main Coast Predict assembly, there will be a presentation on flame, and there will also be a breakout session related to flame. The date here is wrong. I think it's Wednesday in the morning. And I will conclude with showing our faces. So these people are the steering committee of Flame. A lot of us are here in person today, like, for example, me, Georgia, Alfonso, Jason, and Paul. And Clotilde is also joining us online from Australia. So please, if you have any questions about Flame, if you just want to introduce yourself, just come and speak to us. We're very happy to interact both during the workshop and during the main Coast Predict assembly. So I will stop here. Thank you very much again for coming, and Jason will give his presentation now.
Thank you, Anna. Yeah. Well, good morning. Good morning, everyone. So I'm Jason Holt from the National Oceanography Centre. And so I'm going to be talking a little bit about future projections, climate projections in the global coastal ocean. And thank you, Anna, for that brilliant introduction. And thank you, Nadia and the Coast Predict for having the Flame conference, Flame workshop here in the Coast Predict, just before the Coast Predict General Assembly. So future climate downscaling in the coastal ocean. So this started, the Flame project started with a workshop in Liverpool back in 2023. So many of you were there. Unfortunately, we were limited to about 60 people, so a lot of people weren't there. And it's really gratifying to see a much larger group gathering here, both in person and online. So coming out of that discussion in Liverpool in 2023, we've developed a community paper setting out the general envelopes of what we need to consider in downscaling information to the coastal ocean on global scales, and that was submitted to Progress in Oceanography, I think, was the second paper this year, so early in January, with around 40 co-authors in that. And I'm going to give you just a quick run through of some of the considerations in that paper. Hello? Is that better? Okay. Okay. So starting from societal drivers. So the point here is that coastal communities and the blue economy generally require the information about what's emerging in terms of climate change in the coastal ocean and kind of how that potentially changes into the future. To my mind, I think it's helpful to split this into 3 categories. So ecosystem services, marine economies, and coastal hazards. And kind of accepting that these all interact, but understanding how climate change impacts all of these systems together, I think is particularly helpful when perhaps they may generally be seen in isolation. So the question here is, how do we fill the gap that Anna highlighted between the information that's provided by global climate models and what's required at the coastal scale. And this is generally done by some process of downscaling. And so that's illustrated on the right there with a figure from Liz Drenkard's paper in 2021. So that work was particularly focusing on living marine resources and downscaling to support that. And so on the left column, you'll see 3 examples of Earth system model outputs in different sea regions around the world. And on the right, 3 different downscalings associated with them. And you can see quite immediately that the responses in the downscaled models differ qualitatively and quantitatively from what you get from the global models. So you can't understand the processes in the coastal ocean simply by looking at global models. You need to introduce new scales and new processes. And coastal downscaling generally aims to fill, to kind of close that gap between the two. But this is usually done independently by people working, with a grid, maybe some coordination, but generally in isolation. So improved harmonization would generally allow the ability to do sectorial and cross-sectorial risk assessments. So potentially feeding much more strongly into assessment reports, for example, for the IPCC, building better understanding and also building capacity in underrepresented areas. So at the beginning of Flame, we tried to map out all the different connected components that were needed to go from what a stakeholder driver might be at the top to what actionable knowledge might look like at the bottom. And I don't expect you to go through this diagram in detail, but you'll see that it's an immensely complicated set of interacting elements there. And one thing I particularly want to highlight is each of the boxes here is loosely a different community of practice. So it's not only lots of different connected elements, it's lots of different connected scientific communities that need to interact, and they possibly don't traditionally interact together as well as they might. So for example, in the top left there, we have the community that develops emission scenarios. They don't generally interact particularly with the people who do coastal ocean downscaling, in my experience. And so how do we build the better connections between these kind of diverse range of communities as well as scientific practices? So then there's the question of scale. So scale is one of the biggest challenges in this. If we start up at the global scale, the models of CMIP at the moment are still typically of the order of 1/4 to 1 degree, so 25 to 100 kilometers, which in itself is a great improvement on previous models, but is not at all the scale that we need to represent the coastal ocean processes. And so again, it's helpful to consider a hierarchy of scales through the regional, sub-regional, and local, so refining down to scales of maybe order of 100 meters. And as you go down that cascade of scale, the computational requirement increases massively, and so do new processes become introduced. So it's not just a matter of scales, but also the fact that as you refine models, then you get new processes introduced as well, such as tides and benthic processes. And so the kind of things we might be wanting to include in a coastal ocean downscaling effort is kind of summarized in this picture here. But the thing to emphasize is that the climate change comes in at the coastal ocean from probably three different directions. It comes in from the open ocean, from the atmosphere, and also from the land. And so those external conditions need to be well prescribed in any situation. So there are many different approaches to coastal ocean downscaling. So generally what we're talking about is driving high resolution, either regional or global models with outputs from global Earth system models. So at the basic level, well, we could just use the output from the Earth system model, or then, can you see the cursor here? Yeah, the first example, we could drive a global ocean-only model with output from an Earth system model to provide a better better process representation and high resolution. Or we could drive a regional model with output from the Earth system model. We could do the double downscaling to a global high resolution model and then to a regional model, or we could introduce different levels of atmospheric forcing, so either coupled or uncoupled downscaled atmospheric conditions as well. So, for example, drawing on the Cordex program. So what this allows us to do is both improve our geographical representation and also improve process representation. So it allows us to include processes that wouldn't generally fit into a global Earth system model. So as part of this process, we've looked at what downscaling work has been going on around the world. So this map is simply counting the numbers of papers that we were able to find in each large marine ecosystem that has done some kind of downscaling work, and then mapping them in coastal regions around the world. And what immediately jumps out is, just in terms of numbers of studies, is that Europe and North America are very well covered, but there are regions around the world that there have been a few or possibly no coastal ocean downscaling conducted at all. And one of the objectives of the Flame project is to try and kind of fill in the gaps in this map here. We have to accept this is a very crude representation, and it may well be missing a lot of studies, but it's what we could find in the literature over the course of this study. So just stepping through some of the considerations needed for coastal downscaling that relate to those three different kind of clusters of societal drivers that I started with, kind of looking at downscaling for ecosystem services. So for this, you might be thinking, from a European perspective, on things like maintaining good environmental status into the future, maintaining living marine resources, doing assessing the carbon sequestration in the coastal ocean. And generally, these models would involve coupling to biogeochemistry, and particularly that would lead to the complex ocean boundary conditions and land boundary conditions needing to be prescribed. And that would then direct us to a particular class of Earth system models to include marine biogeochemistry to provide those boundary conditions, or else to encourage the use of global forced models to provide ecosystem boundary conditions in the coastal ocean. And similarly complex riverine inputs for things like nutrients. And then again, these models would tend to link to higher trophic levels through other modeling approaches. And so I've illustrated this in quite a novel, quite a new and novel effort. And this is from the ICON coast model. So this is a global forced model, but with a variable resolution and in the coast, and including coastal ocean processes. So this is then in this example is showing the ocean atmosphere CO2 flux during the 20th century. So not necessarily a downscaling case, but it does illustrate another aspect that we haven't touched on here, and that is the upscaling question. So how does the coastal ocean feed back onto the global system, and models like this can actually treat that directly. So the other questions are around coastal hazards, and particularly here thinking about flooding, erosion, and coastal salinization. So here, what is really required is high resolution forcing data, both in terms of time and space. So storm resolving climate models, generally from high-res MIP or from the Cordex program. These models require a treatment of sea level rise. So CMIP models don't in themselves include sea level, all the components of sea level. So that needs to be added in addition. And then dynamically coupling between the components, between sea level rise, storm surges, and waves is really important in these. And again, linking to other downstream models. And I've illustrated this on the right with a study in, I think this is the Po River Delta in China, looking at the impact of sea level rise on storm surge amplitude. And the interesting thing there is that sea level rise in this case would tend to decrease the storm level, the storm surge amplitude, simply by giving more water for the wind stress to move, which is countering the statistical tendency of sea level rise to increase the return period of particular extreme storm events. So the last one here is looking at the marine economies and downscaling for the marine economy, and taking fisheries as an example here, although there are many other aspects of the marine economy we might want to consider. Again, the models for this will be very similar to what you might use for the ecosystem services or the coastal hazards. But here we have complex scenarios for future human activity to take into account. So if we're interested in food resources, for example, into the future, then you might need to consider scenarios for fishing activity, for example. And again, multiple linked models of other components need to be considered. So the example up here is from the Californian coastal system, downscaling that both through the coastal ocean and biogeochemical modeling, but also through to biological, social, and economics models, all linked in a complex modeling chain and different outputs of user value at the end there. So that leads to the key question of uncertainty. So in whatever we do here, there is no real right answer in future climate projections. So uncertainty is quite usefully divided into uncertainty around future scenarios, those emission scenarios that we're considering. Our modeling choices will all add different levels of uncertainty. So if we use a different model, we'll get a different answer, and there's uncertainty associated with that. And natural variability gives uncertainty in our ability to distinguish climate change from what's changing naturally. This is quite helpfully divided, kind of Hawkins and Sutton approach in this slide here, and you see essentially that the scenario uncertainty in green in the middle will tend to. Oh, thank you. That helps. The scenario uncertainty. Yeah. What's around? Oh, yeah. Okay. The scenario uncertainty in green here will tend to increase into the future as the kind of what emissions happen into the future becomes less uncertain. But the relative contribution of the model uncertainty stays about the same, but the variability uncertainty tends to decrease. And so depending on your future time horizon, then you have a different balance of what's uncertain, what uncertainty you need to particularly worry about. And what's particularly important to bear in mind is that if we're looking at multiple linked chains of models, then our estimate of the uncertainty associated with those becomes increasingly complex and unreliable. And that may lead us to take what might be called a storyline approach rather than a probabilistic approach. So rather than trying to multiply lots of uncertainties together that may be highly unreliable, it might be better to simply paint a plausible picture of the future, but without necessarily trying to ascertain the likelihood for that, as you would do in the emission scenario case itself. So this leads to a wide range of different questions in terms of formulating model experiments that we would want to develop for this. So our scenario selection, our forcing selection, how we implement the forcing in terms of the protocol, the simulation periods, can we, and is it realistic to do transient 100-year simulations at the finest coastal scales? And then in small letters in the bottom here, but possibly the most important, is actually how do we build confidence in what we produce of this, and how do we provide validation? So the kind of questions we're looking to explore in this workshop is how do we harmonise the approaches to span these design questions that cross multiple societal drivers? So at the end of the paper, we came up with a proposed framework for a global coastal ocean model into comparison project, GCO MIP, and 4 strands in that framework. So the first, most simply, is actually gathering common metadata, assessment and diagnostics for the models so that we have traceable and reproducible simulations. So even this would be a great step forward to the common way we have of describing downscaling simulation at the moment, which is essentially the method sections in journal papers, which is not the most harmonized way of doing things. So the second strand is then introducing standard sets of model experiments, so having common sets of forcing and scenarios, common simulation strategies, and these can then be applied to any region or for global models. The third strand then requires slightly more commitment, and this is to introduce standard model regions. So essentially case studies of example regions around the world that would provide at regional, sub-regional, and local scale kind of examples of climate downscaling that span typologies of regions that behave in similar ways. And finally, understanding how we actually disseminate to end users and communicate the outputs of these. So sharing the best practice for these, I think, is something that could be well harmonized as well, including the treatment of uncertainty and potentially introducing non-probabilistic approaches to that. So that's all from me. So exploring this is a subject of this workshop. I'm happy to take a couple of quick questions if you have time. But I don't want to use that as an opportunity to do the workshop kind of in plenary. So, are there any quick questions? Yeah.
Thank you. One quick question, some very question. Else we'll be breakout rooms.
Thank you, Jason.
Thank you,
visionary and important. Excellent. My question is if you could introduce also some thinking about observations that are required for getting these trusted models. So we are heavily we are heavily involved into getting observations at the coast.
Yep.
That will add reanalysis, whatever. So what is your thinking?
I think that is a key element, and I think it is that there is a need to define the best practice in terms of actually the validation approaches itself, because it is not straightforward, and then from that the observations are required to drive to drive that. But we can learn an awful lot from operational oceanography in that. Yeah.
Thank you, Nadia. Okay, we can move on to the case studies now, and the first presenter will be Giorgia Veri.
La faccio partire io. Okay, perfect. Okay, good morning, everybody. This is Giorgia Verri from CMCC Foundation. So this talk is about the experience that we collected within a couple of recent projects and within and under the umbrella of the FLAME initiatives. So we had the chance to perform a limited area climate downscaling over the Adriatic Sea. We collected many new insights about the future climate of the Adriatic Basin. This was possible to the strong interaction among the institutes involved in these activities. And actually, I'm going to focus on few insights among the ones that we gathered during these projects. So I invite you all to have a look also of other results that came out during these activities, and to have a look of the special issue that have been released within AdriaClean project. So first of all, the motivation. We are speaking of the Adriatic Sea, which is the first pilot site we are going to discuss today. This is a semi-enclosed sea within the broader, the bigger Mediterranean Sea. They are both semi-enclosed basin, but while the Mediterranean is known as a concentration basin, the Adriatic Sea is a dilution basin, which means that, and this is basically the first scientific question, we expect that air sea and land sea fluxes in terms of fresh water may play a significant role with respect to the Adriatic future climate. And we are interested to know more about that to advance our knowledge on the Adriatic future climate. In particular, looking at the freshwater effect, the role they may play on the local sea level rise. And moving to the very local scale, thinking of transitional areas and in particular the estuaries, the second scientific question is about how multi-physics stressor, like decreasing runoff or increasing sea level rise, may interplay, combine in a nonlinear way, and determine the evolution of the lens interface. Moving to our experience in terms of sub-regional and coastal climate downscaling, this is a sketch of how we proceed. Our starting point is represented by an existing regional climate model within the MedCordex framework, which is a couple ocean atmospheric model. What we did, we nested our limited area climate system within this existing regional climate model. And the keywords in our activity were basically to reach a very high resolution, never reached before over our area of interest, to take care of the downscaling ratio between the driving climate forcing and our sub-regional system, and to provide an integrated multimodal system which can solve in a more comprehensive way the coastal water cycle. So this was probably one of the first attempts in terms of limited area climate downscaling over the Adriatic region. In addition to that, we were able to reach a very local scale with a hyper resolution in the pilots that have been identified as hotspots for climate change. So thinking of these keywords, the first is a high resolution, which means a time and space resolution. And here you can see a video from a PhD project from Renata Haidt PhD project, which is quite illustrative, but it is very interesting for modeling practitioners, because it basically says that 2 kilometers is the resolution that is required over this area, the Adriatic Sea, if we want to solve the mesoscale, and we know that according to the Rossby radius, but also if we want to properly capture the water exchange to the narrow Otranto Strait, while we totally fail or partially fail if we limit the resolution of our model to 6 kilometers. And this is because of the cross-scale processes that occur at the strait, which also determine backward effect on the large scale and then on the water exchange to the strait. In fact, in the middle, you can see a different approach, a statistical approach, which basically just apply a low-pass filter on a spatial scale lower than 10 kilometers. And with this statistical approach, we are still able to identify the salt water entering through the strait, while we fail with a deterministic 6 kilometers. So this is a way to stress how the resolution play a significant role in the downscaling approach, should be considered carefully. The other keyword for today's discussion is the integrated modeling we are asked to ensure in order to solve the coastal water cycle. And in our case, an asset of the downscaled system is represented by the hydrological component, which is based on WRF hydro system. And as you can see from this sketch, the WRF hydro system consists of many modules, which basically allow to solve both the vertical and the lateral routing of surface water and subsurface water. And at the end, we were able to prognostically solve all the catchments that surround the Adriatic Sea, which are about 145. And there was a quite demanding corresponding calibration phase. Here I just put as an example the calibration phase that is required to properly capture the basin cumulative rainfall and the reverse inflow. But at the end, with this prognostical representation of all the catchments, we could provide the full representation of the coastal water cycle and the feedback that hydrology may play on the Adriatic circulation and dynamics. So we start with a simple comparison between our driving climate model and our downscaled system over the Adriatic Sea. And here I just put a few pictures to show you the added value of reaching a higher resolution and of using an integrated approach over a sub-regional area. So as you can see, if we assume reanalysis as our benchmark, and if we compare the performance of the driving Med-Cortex regional climate model and the downscaled sub-regional system, we can appreciate the improvement in terms of stratification of the water column. We increase the stratification of the entire basin, and we are close to the analysis, and we improve also the capability to represent the salt content of the Adriatic basin, again, being closer to the reanalysis, which are our benchmark. So according to the hydrological component, WRF hydro-based, the climate projection that we release with this sub-regional climate system give us an important information in terms of what we should expect as the total river release into the Adriatic basin in the mid-term future by 2050. So our modeling results say that the total river release is expected to decrease of about 35%, with this difference between the rivers ending on the eastern and western side of the Adriatic Sea. So the ice decrease is expected from the rivers inflow ending into the western side, including the Po River. And looking at the other freshwater fluxes, so in terms of latent heat flux, what we expect in the mid-term future till 2050 is a seasonal decrease through all season, through the entire basin of the latent heat, which means, in other words, an increasing evaporation. And in terms of total precipitation, the behavior is more heterogeneous on seasonal basis, but we can distinguish a decrease in total precipitation across the Italian peninsula through all seasons. So based on these results, our question is how these changes in terms of freshwater fluxes, evaporation, precipitation, runoff may affect the Adriatic thermoline characteristic and the Adriatic future climate. So starting from the same analysis, seasonal changes in terms of sea surface salinity, our climate downscaling basically say that we should expect a quite homogeneous increase in terms of temperature across all basin, across all season, while in terms of sea surface salinity, the behavior is more heterogeneous, and the highest increase in terms of salinity is expected in the northern Adriatic and along the area of freshwater, runoff freshwater influence. Finally, the bottom panel show the maximum Brunt-Väisälä frequency at the top 100 meters of the water column, which is basically the result of the previous ones. So we should expect a decrease of stratification, especially in the northern Adriatic and along the main region of runoff freshwater influence. But there is also a clear distinction between northern and southern Adriatic in terms of future climate. So we can summarize these results saying basically that salinization is expected to prevail on the heating in the northern Adriatic for the mid-term future. And this means that we are losing stratification. We will lose stratification in the northern Adriatic. In the southern Adriatic, the behavior is a bit more complex, and eventually the heating effect may prevail on salinization and may eventually increase the stratification on seasonal basis, for example, on winter time. Based on this result, we extend our analysis to the entire water column, and we look at the expected stratification for the two sub-basins. As you can see on the left side of the slide, this is the Brunto-Vaisala frequency for the two sub-basins, Northern Adriatic and Southern Adriatic. The projection range is in blue, the historical range is in black. So in the Northern Adriatic, the loss of stratification characterized the entire water column. And this means, for example, in terms of dense water formation, that we should expect a strong increase of local dense water, more than 100%, while in the Southern Adriatic, the expected changes will be a bit more complex, with, again, a loss of stratification at the top of 200 meters, but an increase of stratification at intermediate and deep water column. This in turn means that then, looking at the Southern Adriatic, dense water are expected to decrease, and this is the result of more than one driving mechanism. So while probably in the Northern Adriatic, our conclusion is that the future changes in terms of stratification, then the dense water, are mainly driven by the buoyancy loss at the surface. In the Southern Adriatic, the future changes in terms of stratification, dense water formation, are a nonlinear combination of multiple drivers. So not only the buoyancy loss at the surface, but also changing water entering through the Otranto Strait, and the heating effect that still prevail at intermediate to deep water column. So thinking of the Otranto Strait, you can find more results in our paper, but I want just to point the attention on this picture, which is a cross-section of salinity at the Otranto Strait. This is a seasonal change in summertime, and what we should expect in the mid-term future is a freshening of the inflowing water through the Otranto Strait, which is consistent with other studies saying that the Levantine intermediate water are expected to decrease in the next future. So these results in terms of stratification are then expected to affect also the sea level rise, which is one of the pressing issues for the Adriatic Basin. And here is the analysis of the seasonal change in terms of sea level for the Adriatic Basin. This panel refers to the only mass component, which is the incompressible component solved by the ocean model, so the first two terms of the total sea level equation. And basically, this is the component driven by freshwater fluxes, gain or loss at air-sea length interface, and the freshwater fluxes exchange through the Otranto Strait. So the mass component is expected to decrease in a quite homogeneous way across the basin, with the highest effect in the Northern Adriatic. And this is easily justified in terms of the decreasing freshwater flux at air-sea and length interface, precipitation, runoff, and evaporation, but can be also explained looking at the net outflow to the Otranto Strait, which is found to decrease in the projection range respect to the historical range, but not enough to compensate the freshwater loss in the inner basin. So when we consider also, here we are, we are ignoring the density changes, which represent what is called the steric component of the total sea level rise. If we account for them, the result is totally different. So here is actually the Adriatic total sea level, including both mass and steric component. As you can see, what we should expect is a clear sea level rise across all seasons, with the only exception of the Northern Adriatic. So this is a quite new result with respect to the state of art, which was made possible probably by this integrated approach to solve the coastal water cycle, accounting for the feedback from freshwater fluxes. And what we can conclude according to these results is that the sea level trend in the Southern Adriatic, but also in the Northern Adriatic, is driven by the steric component. The thermosteric component in the Southern Adriatic determine the sea level rise, allosteric component in the Northern Adriatic, which may eventually determine a negative trend on seasonal basis. There is a key role when we speak of allosteric component played by the river runoff, which is expected to decrease, as we said, and which is expected to contribute to the allosteric term besides the mass component. Just to conclude with analysis of this picture, we have to consider that these results are not accounting for the subsidence, which may play a relevant role in the Adriatic. This was demonstrated in recent publication about how the subsidence may strongly condition the relative sea level rise in the Northern Adriatic. So eventually the relative sea level rise could be positive even in the Northern Adriatic. Anyhow, what came out from our, downscaling exercise, a quite new result, is about the spatial variability of the sea level rise in the Adriatic Sea and the slowdown in the sea level trend across the entire basin. This is, we could say this is a new result with respect to the state of art, which is based on global and regional climate models with not enough horizontal resolution and not enough comprehensive representation of all the processes that determine the coastal water cycle. There was a paper published a few days ago, which I would say corroborate our results. It is only based on satellite altimeter area analysis, and it basically provides an evidence of the heterogeneous behavior of sea level rise across the Mediterranean subbasin with a key role played by the steric component. And if we focus on the Adriatic Sea, it is clear the trend slowed down across the last 3 decades with a negative trend over the last decade. Maybe I have not enough time to go. Okay. Because, as I mentioned at the beginning, a second scientific question is about the very local scale, the transitional areas, where we are asked to reach extremely high resolution if we want to account for the climate changes impacts. This is a focus on the strategy adopted for 2 estuarine areas, which are the Ofanto, and then I will show you the Po Delta case. This is the Ofanto estuary case. And as you can see, our downscaling strategy consists of merged approach between a 3D finite element modeling of the river sea continuum and a column-only analytical model, a box model showing the estuarine dynamics. So with this merged approach, we are able to provide long-term projection of salt wedge intrusion and net release at the river mouth in terms of volume flux, temperature, salinity. What came out from this downscaling approach, downscaling strategy, looking at the midterm future till 2050, is that the salt wedge intrusion is expected to increase along the Ofanto estuary up to more than 100% on annual basis, and also the river mouth salinity is expected to increase. But what is interesting is that focusing on summertime, when we observe the highest increase of salt wedge intrusion, we also observe the lowest increase in terms of salinity. This is not a paradox, but this is explained with the increasing stratification along the estuary. This is a particularly shallow estuary, so it is particularly sensitive to the sea level rise. And the effect of sea level rise is to increase the stratification, which means a higher salt wedge intrusion, but also a more tilted salinity profile with the fresh water remaining at the top at the river mouth. A different case study is the Po Delta, which is instead river-dominated estuary. Here we follow the same downscaling strategy, combining 3D unstructured grid modeling with the 1D box modeling approach. And what came out is that for this specific case, in order to appreciate the effect of the sea level rise, we have to look at long-term projection till 2100. While, for example, of the historical range, the sea level level rise is found not to play a role because it is totally driven, the salt wedge intrusion is totally driven by the runoff decrease. So the main insight which came out from this downscaling exercise is about the non-linear combination of runoff decrease and sea level rise with respect to the increasing salt wedge intrusion for the Po delta, where again runoff is expected to play the key role till the long-term projection when it will be low enough to make the sea level rise the main driver. Okay, this is the overview of our activities in terms of sub-regional and coastal climate downscaling. I summarize here the main insights that I told you, and if you're interested, you can find also the main reference that I mentioned. And as I said at the very beginning, there is also a special issue where we published 12 articles with all the main insights that came out from this coastal climate downscaling. Thank you.
We have time for one quick question.
Wow.
Oh, you raised your hand first, so. Okay,
Just a quick question is, in the eastern side of the Adriatic, underground water, you have a lot of underground water coming out there. Is that included in your model? And how will that change and affect your results?
Yeah, this is, let's say, work in progress, meaning that our hydrological model is able to solve the groundwater, including the mechanism of recharge, discharge of the aquifers. What is still ongoing is to solve the feedback between groundwater and marine water, because so far there is like a wall, so the groundwater cannot speak directly with the marine water. So the land waters are fully coupled in two-way mode. So there is a two-way feedback between land surface water and groundwater, while looking at the marine side, the feedback is just one way, and it is coming only from the land surface. So there is still a close boundary between groundwater and marine water. But we know that in the Adriatic Sea, this feedback may play a role. I read something about 20% of total runoff in the Adriatic Sea coming from groundwater. So this means that we have work for the future.
Okay, quick one, just inquiry. So you use the WRF model for to get the surface boundary condition to force the model for the future projection scenario, and you use the worst scenario RCP 8.5.
Yeah, I forgot to mention. Yeah.
Yeah, and so you have you mentioned that the precipitation you found it's less, but elsewhere when using the RCP 8.5 it's increased. The precipitation elsewhere it's increased. So can you say why, especially in your scenario, is decreased for the precipitation? That's one question. The second one is for the Po River. What projection did you use? Did you use climatology for projection, or you used something parameterization for Po River for the RCP 8.5 scenario?
Okay, so regarding the first question, okay, our multi-model system include the WRF for the atmosphere, WRF hydro for the hydrology, and basically NEMO for the ocean. I forgot to mention. So, and we are within RCP 8.5. So, our result is consistent also with our driving climate model, which is MedCordex in terms of precipitation over the Italian peninsula. And according to the way WRF is able to solve the convection and cumulus schemes, these are our results. I think at least for the Central Europe, it is not inconsistent with other recent studies. I don't know. I ask also the colleagues.
rising temperatures over snow accumulation. So it's combined issue.
The discussion offline, so we can move to our next presentation. Thank you very much, Georgia, again. So our next presenter is Joanna Staneva from Hereon.
Okay, then good morning, everyone. I have been asked by Anna and Jason to give some illustration of our coastal downscaling climate scenario that we have recently made, and also to provide information about the approach, how one is doing coastal downscaling, especially for the estuaries. And this is why I decided to showcase you two completely different estuaries. One is in the North Sea, which is tidally driven one, and the second one is in the Baltic Sea with a very strong stratification, but also to give you some illustration of what are the most important processes that need to be considered. But first, why are the estuaries so important under the climate change, and why we also need a special attention on the estuaries and different approaches compared to the global or even to the regional scales? Because we know that the sea level rise and the climate change, they really impact the shape and biological nature and even the form of the estuaries. We also know that the estuaries processes are interconnected and much complex because also the land ocean continuum has to be considered. And also there is a very strong interlinkages and feedbacks in the estuaries that are also very important if we are about to do the climate change simulations. And here we are on a climate meeting, and you know that the impact on climate change and the sea level rise, they can be twofold. The one can be the direct impact, for example, changing the volume due to the river runoff, due to the participation. But then there is a lot of indirect impact, for example, changing the vegetation or changing the sediment transport. And then we are trying also to develop methodology that covers that. But very briefly, how do the estuaries impact on the sea level rise or in the climate change as a general? It can be done through changing the coastal erosion, because the sea level rise and the climate change actually impacts and affects the coastal erosion, or reducing drainage and prolonged inundation in the estuaries, or saltwater intrusions. It has been also a showcase by Jason already. Changes of the nutrient dynamics due to the climate change is important. Changes of the vegetation distribution, which can be also direct or indirect change, or changes in the tidal range, because also when we change the physics and the processes, then it will feedback not only the physical changes, but also the biochemistry, or sediment transport, which again can influence changing the processes, or also the ecosystem habitats. Don't worry, I'm not going to talk about all these 8 items because we will need maybe a full day, but I will just cover very few of them. But in order to address this, we need models. But in order to have these estuary and coastal models that actually assess the climate change or sea level range, we need also to have the feedback from the land from one side and the open ocean from the other side. Therefore, the models, they have to be linked with the hydrology, the land, they have to be linked with the regional or global if we have good data. But it is also not trivial. I will show you why, because most of them, they even don't consider the sea level change, and this has to be added extra. But we have also to consider the interaction between the different components, like not only hydrology and coastal, but atmosphere, ocean, or the waves. I will showcase showcase why also the waves are important. Also, they are neglected for many of the climate change scenarios. We have also models at the different scales, starting from the regional, then to the basin scales, but we are really interested at the end of the day what is happening in the estuaries or what is happening in the harbor. And this is where we really then need to go for a very fine scale and the resolutions. Regarding also Nadia's questions, the models are nothing if the synergy between the observational data and the models are not secure. And we also have to communicate uncertainties in a better and correct way. We have to solve practical problems with those models. They are also nice tools, but they have to solve the different practical application. This is why interconnections between biochemistry and vegetation is needed. And they have to focus on the human ecological values in the change of the estuaries management and the sea level rise. Therefore, also the management's mitigation. But nowadays, we are talking more adaptation is very important. And in that respect, also to meet the end users and society needs and demands. And in order to do that, we are continuously developing our coupled coastal system, which is the regional and coastal. This is the GCAS coastal system, which actually considers the interaction between the atmosphere, hydrology, waves, and ocean from one side, but also the dynamics of the fluxes from the land to sea from another side, and the coupling of marine hydrosphere and the biosphere. And very briefly about the methodology, first starting from the regional case, it is a bit of a complex interactions from the global, the regional climate model, then connecting with the different couplers between the ocean, the wave, and hydrology models, and also the tidal components in order to have all these components interacted in a proper way. And as I have been also asked to show a bit about the impact of the waves regarding to the breakout discussion that we will follow up very briefly. Waves had been forgotten for a long time, but recently the waves are important not only for the short-term prediction, but they have to be also considered for the climate applications and studies. And as an example, why they are important, if we are talking about extreme events and hazards within the climate change, then we can see that considering or neglecting the waves can change the story and the simulations. And this example here shows the surge components in the Hamburg area. This is in the German Bight area. And we see that considering the wave-ocean interaction comes to almost 0.5 meter difference in the storm surge. And the most important is that the most of the differences occur in the coastal areas. And this is the areas where the population lives and we are interested. But if we also look at the spectral coherence, we have done it. I will provide you with some references so you can read about the details. We have also seen that the coupling affects both scales, the large scales, which is above 200 kilometers, but also the small scales, but also the coupling with waves affects not only the surges components, but as well as the average one. And this is several decades of averages of the coupled and uncoupled model for the 95 percentile. And you can nicely see that the most of the difference, which are also 20% in the relative differences occur up to the coastal area. And then moving from the regional to the estuary scales, here this is the methodology that we have developed in order to try to consider as many as possible processes and to study the impact of climate change on the estuaries. We have to take into consideration the sea level rise. This is why the mean sea level rise, according to the PAUMA approach, has been taken from the global and regional sea level information. Then we proceed with the two-dimensional runs, because if we are doing the estuaries, we need a forcing which is with a much higher resolution than it is available from the climate projections from the global. This is why we do also the two-dimensional runs, which provides hourly barotropic currents for the three-dimensional runs. And then we use these three-dimensional runs using hydrodynamics, waves, ecosystem models, and then at the end I will show you some vegetation example. And I showcase this, as I already announced, in the two areas. This is in Europe, the North Sea, the Baltic Sea, and more specifically, I will just give you illustration of the German Bight in the North Sea, and this is the Elbe with the Hamburg harbor, and the other area which is also very interesting, this is in the Baltic, and the Baltic is connected with the North Sea, but through these very shallow connections, here we don't have tidal forcing anymore. And this is the Odra Delta estuary. And in addition to the hydrodynamics and waves under the climate change, we also do the biogeochemical model. And this biogeochemical ecosmo model is also coupled through FABM coupler with all these estuary models. Therefore, we assess the impact of the climate change, not only on the physical components, but also on the biogeochemistry. Before doing whatever impact is and the differences of the future minus past climate and assessing the changes, as already discussed a lot, it is important to assess our models and to have models that are reasonably good to be used also as a tool for climate change studies. And here we did observations, not only for the physical components along the estuary. This is the Elbe estuary, and we actually assess the velocity, we assess the sea level, but also we assess the biochemical components like dissolved organic and nitrogens to see that our model is doing in the nowcast, hindcast reasonably well. And we were satisfied with the results even in the deeper estuary. And then we say we can then use the same model configurations with all this setting up of the parameters for the climate projections. And then very briefly, about the response, I will start with the physical component, and then we'll show you very briefly example of the biogeochemical component of the response, and we'll provide at the end list of the references, and if you are interested in one or another, you can then refer to that. And here we start with the simpler one, the sea level, but sea level also including the tides, and we assess also the decadal sea level change along the whole Elbe estuary. We did that also for the other estuary, in which we haven't had only one single climate change projections, but in order to study the internal variability due to the climate change, we also did some ensemble simulations. And here you can see the differences in the several points from the mean, but also from the ensemble for the spread, because it is crucial importance if we are talking on the estuaries and if we are talking on the climate change, not only to provide trends and the data, but also to provide measures of the uncertainties. And looking at the mean water level of the empty amplitudes, but also in the maximum water level, we can see that the spread of the mean water level is basically dominant by the spread of the global sea level rise, which is something to be expected. The global sea level rise is transferred to the local and then to the estuaries. But what is also important is that we have seen that the tide sensors are very sensitive to the internal variability in the estuary as well. So it is not just simply transferred from the global to regional to the estuary, but also the internal variability of the geographical domains are very important. If we are looking looking at the different estuaries, we will see completely different response and different changes of the sea level rise. But also what is very important is that the monthly maximum, as it can be seen here, but also the extreme water level, which responds to the mean sea level rise spread along the area in a different way. So if we see dot, we have the trend, those trends are different and the spread of those trends are different, but also that the internal variability that has been studied, if we do the ensemble simulations, they are dominant within the estuaries. And this is why we concluded that the future search levels are driven by both the mean sea level rise, but the internal climate variability. Therefore, the internal climate variability is not to be neglected in the future coastal and regional projection, especially if we want to focus really to assess the impact of sea level rise, the impact of climate change on the temperature. Another results comparing Elbe and Odra. There are several publications, but I put it in one. This is how the climate change experiment changes the physical components, the temperature and the salinity, but also the stratification. I already mentioned those are two completely different estuaries. The one is tidally driven. The second one is based on the stratification, but both have also the impact of the fresh water from the rivers, as well as the impact, which is completely different. This one is in the open sea. This one is the semi-enclosed, almost enclosed, the Baltic Sea responses. Not a surprise is that the temperature changes with the climate change. We have, however, the different changes of the salinity due to the climate change. This is 8.5 experiment, but we did it with several others. But also something to give a message taking home, not to be neglected, is most of those studies show always the distribution and the two-dimensional, but this climate change and the sea level rises and change, they do also impact and influence the distribution in the verticals along the Elbe estuary. And we can see that what is seen on the sea surface can be completely different on what is seen within the mixed layer or what is seen in the bottom of the estuaries. This is why it is also crucial when we are looking at the sea level change in the estuaries, also to look at the vertical structure. And then we see that the mixing, the stratification changes completely differently if we are doing that along the estuary or if we are just very close to the coast. Then moving from the physics very quickly to the biogeochemistry for again the both estuaries, we can see the shifts in the biogeochemistry due to the climate change. We can in overall see for the close Baltic Sea with the Odra estuary, the increase of the phytoplankton, while looking at the Elbe estuary, this is not trivial. We have, in general, decrease of the phytoplankton along the river process. I'm almost ending. And then we have overall decrease of the oxygens, but also the hotspot and the oxygen minimum zones. They were shifted in the different experiments. And very briefly from physics, biogeochemistry, let's move to some indirect impact. And within the European Green Deal project, RESCOS, we are studying the impact of the vegetation and the seagrass, and also how the climate change would actually influence us and whether the nature-based solutions can help within the climate change. And we produce several what-if scenarios for the coastal protections in order to assess to what extent the vegetation could help and mitigate the sea level rise within the climate change within the estuaries. I'm not going into details with that, but what we have done is several experiments with and without seagrass within the climate change context, in which we run the coastal models with and without seagrass for the future and also for the past. And then we assess the impacts. And this is a bit of complicated figures, but it shows basically the difference with and without seagrass and with and without sediment dynamics in the future and in the past. The future, this is the 90 and the past. And in overall, it can be concluded that for the future projection, the seagrass restoration analysis bring the added value, and then also the overall efficiency of the kinematic due to the seagrass, which is the reduction of the wave action and the wave energy with the sea level rise is very important. In addition to that, we did also the habitat mapping approach, in which we added the EcoSim, which is the habitat map model, and then we also at the end assess what are the changes of the habitat and the habitat concentrations within the sea level rise. And we see that there are quite significant changes in the habitats with or without also the existence of the sea level grass. Here we are in the ocean decade project. This means that what we are doing and working has to be transferable to another basins. I showed you only two showcases. The one was for the North Sea, the other one was for the Baltic. But similar approaches we have already implemented, or we are currently implementing within several activities in some other areas within Europe, like the Black Sea region, but also in several other areas. We do experiments within the East China Seas, also with the downscaling approaches. We do experiments for the Southwestern South Atlantic and the Brazil coast, assessing also the impact and the intensity of the waves and the impact on the climate change, going also and assessing what is the importance for the sea level rise and the waves intensification for the coastal erosions in the Brazil coast, or also in the eastern coast of Ghana. And there will be also presentation about that. And just to conclude why this is important, all our studies and all our climate simulations are nothing, and our systems are nothing if they're just for process-oriented studies. Of course, processes are important, but in overall, the end-to-end system, they are important and they are of use only. The multi and transdisciplinary approaches are considered. They are of use only the different sectors also included from the very beginning in the co-design of our simulations and our analysis. It is crucial that early stage researchers and early stage career scientists are involved in the process from the very beginning, but also that's why we are here, the collaborations and the networking among the different institutes, among the different continents is important, because we are stronger if only we work together nicely. This is the list of the publications which I use to show my results. Feel free to have my presentation and then to read for more details and contact of any questions. And I noticed that even the team which was involved from my group for doing these results fits very well with the UN Ocean Decade Cost Predict programs, being really strongly international. Thank you.
We're running a little late, so if we have time for one quick question.
Please, some more details about the space and time resolutions of the different models used.
Yeah, our regional model For the North Sea, the Baltic Sea is with resolution of 3.5 kilometers. Then we are using the unstructured grid models for the German Bight with the resolution of the open area of the 1 kilometer up to 100 meters in the coastal area. But the two estuaries that I have showcased, the Elbe estuary and the Oder, they are with a resolution of 20 meters in the estuary, because this is very important. We also studied how the climate change affects the bathymetry and how also the changes of the channel are important. And here one needs really to go to a very high resolution.
You have time to catch up with Joanna during the whole workshop. You want to discuss more? The University of Alberta.
Good morning, everyone here, and I guess good whatever time zone you are in for those of you online. I took my charge here to talk a bit about some of the technical issues involving some of the downscaling. So I'm going to have maybe a bit less results and a bit more of questions and things one want to think about. And I also wanted to bring in sort of a different region. In Jason's talk, when he showed the coastal environment, he said it was driven from 3 areas: offshore, land, and the surface with the atmosphere. You look carefully, there was a white blob for the ice on top, because there is also on the impact of our sea ice, and especially in high latitude regions, that's very important in how it's changing for its communities, and then how it's affecting the marine system below, and in fact changes in the cryosphere from melting glacial, melting permafrost, that's also putting additional material nutrients in the water, is having broad impacts throughout the marine system. So that's the example. I'm going to be focusing on regions sort of in the Arctic, Northern Canada, and some of the community interactions and questions that one wants to do this type of climate downscaling linked to high resolution marine modeling. So I'll talk briefly about the region, some ocean and biogeochemical modeling aspects we're looking at, the idea of runoff that's come up already, the importance of it, and also the different components and items in the runoff. Talk a bit then about some of the downscaling questions for driving some of these regional models, especially for erosion and impacts on coastal regions, waves, and then getting to, again, how high do you have to get into the spatial resolution, the very high resolution? Where do you nest it? Where do you need that resolution to be able to address, start to address some of these questions? So one of the things in terms of working with coastal modeling, and this came up again in the initial presentations by Anna and Jason, was who are you doing it for, the partners? In Canada, many of the northern communities are indigenous. They're Cree, Inuit, etc. And so we end up doing a lot of work with that. This is from a plot from a study of southern Hudson Bay, James Bay. So we have the globe. It's not very clear, but we go into sort of some of the inland seas of central Canada where there's a number of communities, and they're very much being impacted by climate change in this region. Traditional lifestyles being affected, especially with the loss of sea ice, which is used. And so they're very interested in this work, but there needs to be a lot of collaboration to try to understand what the community is interested in, so that then the studies can focus on that, and as well as what information do you bring back? It's not just output from a climate model. How do you convert that climate model output to, if you want to say, human-related variables that are relevant for communities? And that needs a lot of building of trust, building of interactions beforehand, and it really needs to be a complete aspect where you're going from ship-based observational programs, community-based sampling, so you're also getting the communities involved in the sampling, so they're got a understanding of it, a value in it, they're contributing, linking to the model, so you can then provide that all to the understanding, both of the global system, the regional system, and then actually down to the local system. We've also been doing this, we're working with communities in Northern Canada, so this is now a view going up into the Northern Arctic, where there's also our government is putting up marine conservation areas, and they're very interested in the climate and change impact. How are that going to impact those marine areas, and how do we best define them, and how do we best protect them going into the future? So there's a lot of interest in understanding oceanographic, sea ice, wave, conditions going out to the next century. How does coastal erosion and flooding risk, as well as linked to some of the biogeochemistry and some of the communities. For example, in the next slide, I'm looking at a community that's up in this region in the high Arctic. This is a community of Greaseford or Wiesatuck that's a local Inuit community that very much use the ice for all their traditional lifestyle, but are very concerned about these changes and how that's going to impact them, how it's going to impact their livelihood, their ability to get food and that. And so we need, and especially with the loss of ice. So we're doing a lot of work also with them since getting data. There's issues with product data. So actually training the locals so they can use CTDs, make marine biological measurements. And when they're out on the land doing, say, hunting experiments, hunting trips, they can stop, drill a hole in the ice, collect data, report that, and then continue on their lifestyle, and especially because there's such a lack of data in winter in these regions. And there's a lot of concerns about coastal erosion. And the key thing, again, the communities want these climate studies, they want these regional downscaling done, but they want the results translated to forms they can use, and they want to be involved in the process, and especially their younger people trained so they can be involved in the science. And this is important, again, going to this same region, because it's very interesting, because it's also the significant changes in the marine conditions. This is sort of looking at the upper ocean in this region, going from the 70s up to recent years. And you can see both lots more of there's warming at the surface, generally because of ice coming up, but there's also very cold periods where cold ice is coming from the Arctic because of changes in Arctic mobility, and then tremendous amounts of increased thick layers of warm heat in the deeper layers, which may have then impacted melting tidewater glaciers and leading to feedbacks in the systems. And some of this data, especially the seasonal variability, we wouldn't be seeing without these type of community interactions. And so we want to use this, then integrate and link to the regional modeling system. We've been doing regional modeling sort of in a general region, sort of focusing on the Arctic and the Atlantic, and then putting nests in to, again, downscale for aspects of the archipelago, Hudson Bay regions we're interested in. I forgot to mention the Hudson Bay aspect. One of the other regions there's a lot of interest in the study, there's also for the river aspect, there's a lot of hydropower. And there's wanting to understand what is the relative role of climate change versus river regulation as we go forward into this region. Obviously, biogeochemistry is important, so there's coupling of biogeochemical models into the system, both simplified for long experiments, more complicated ones to look at different approaches. And for the Arctic, we also have to consider the sympagic component of the biogeochemistry. For example, ice algae and how that, as the sea ice changes, how as the light regime changes, that's impacting the system. So these are all aspects that are needed to be considered in, if you want to say, the developing the metrics and the tools that we're using for these regional coastal downscaling studies for the future for the high Arctic. Rivers, of course, are a huge change. The Arctic has got huge drainage basins. Even though the Arctic is the smallest ocean, it's got relatively large river drains draining all over parts of Russia, northern Canada. There's a lot of variability with time coming into this, and these rivers are going to also increase the amount things for further examination. And then again, how do you properly downscale so you represent the features, the orographic winds, the local features that could drive the flow through straits and complex regions that are relevant in our local region. I'm not going to go all the technical details, but this is just showing, this is October fields of temperature and winds. And you can really see how different the scenarios are. So you really can't just pick one or two. You really need an ensemble, and you really need to do some confidence work to try to understand the probabilities, the distributions, what's that telling you about your ensemble results for change in the region. We also said, as we said, erosion was very important in this region, these low-lying Arctic coasts are very sensitive. There's a lot of, and especially the question is, the sea ice comes off, what about storms? So we started to look at also using the ocean model output to drive Wave Watch 3, to look at those wave scenarios, and that could also guide, again, infrastructure in the north. There's a lot of questions related to that. I've only got here results for the validation of the present day. It's presently been run to, again, look at how those significant wave heights are changing going into the future. But this is, for example, just looking at trends over the last 20 years, and this is August and November, and you can really see where it's red, the increase in the significant wave height is very much focused in the high loud regions that are losing its ice, and especially we go into fall. August has sort of always been partly open water in the Arctic, but you get, again, as the less ice, the more waves, the increased erosion, and as the ice-free season gets longer, you start to get significantly more erosion or wave effects as storms propagate into the Arctic as you go forward. Let's see if the movie will play. And this is again just showing aspects of the significant wave height. And again, you'll see as we go in, as the ice retreats, you start to see this penetration of storms, significant wave height farther and farther into the Arctic. Notice the wave height is on the bottom color scale. The right color scale is for the ice fraction. Date is here. I'm not going to play the whole thing for time, but I just want to get into, as the ice starts coming off, you really start to see wave effects that hadn't been before seen, that were much shielded by ice in the Arctic, having much more erosional effects in these regions. I'll just give it another second, or if not, you'll be able to watch this movie afterwards when you play it with the rest of the slides. But again, I should have put it on a faster speed. You're really starting to get these wave heights penetrating in the ice-free region. You can start them seeing affect the coast of Hudson Bay as an example. But for periods of time, for reasons of time, I'll just move on. We're now going up to, again, the question of scales. What about if you start running models at 1 kilometer? And then how do you nest even higher resolution models for regions, ports, communities in that? Because again, those very high resolution gets to represent, just as George was saying earlier, about the role of eddies, the mesoscale. And you really get those features being displayed at the high resolution that you don't in the coarser resolution. And then you could ask, what is that integrated effect? How does that change, again, the role of the mesoscale, the penetration of water mass into regions, say warm water that will affect tidewater glacial melt, different waters with different nutrients will affect the biogeochemistry. All of these are very much questions that we need to answer and understand what resolution can we go to. And of course, running high resolution everywhere is very expensive. So that leads to the idea of nesting. And again, can we nest in the high resolution nest, say in our case from Canada, something that's looking at projects that are trying to downscale all around the oceans around Canada, nest for the Arctic, then put additional second or third twin child nests or even multiple ones at different locations to get different communities down to that resolution they need to understand the effects in their waters, the effects on their sea ice, the effects of the coastal erosions and the waves in those systems. So in summary, I've just presented a mismatch of ideas in one sense, but I really pointed out the importance of, I think, looking at coupled ocean-sized biogeochemistry models that are forced by river runoff, that's including output from hydrological models, not just fresh water, heat, biogeochemistry, nutrients, all those components, looking at with downscale CMET projections, looking at how they'll affect changes in the Arctic, as an example, sea ice, coastal erosion, and running an appropriate ensemble so you can really try to understand the variability, the uncertainty, the likelihood of different changes. And then running at high resolution, you can get the mesoscale, the sub-mesoscale, and how you do that over a whole region versus over the open ocean to provide details to high resolution nests further into the interior, so you can look at community process of fjords or any other region you might be interested in. So I'll just stop here.
We have time for a quick question if one has a very quick question. Nadia.
So thank you so much. Very interesting. And I like a lot your effort to translate toward the local communities. But there is another effort that the decade is going to also try to see, which is talking to investors in restoration. And for that, some of your work, and Joanna and Georgia, is very relevant because they need to know if doing certain actions, you de-risk the investment. So this is actually a lot, that's what they are talking about. And I hope you can pick up also this idea with some of your modeling that could be done in order to answer that question. How de-risking, how much I can de-risk the investment?
It's a different community, like as you said, but it's very relevant, very important. And I think you get to that idea of, again, running ensembles in the, with nests down to the region, in that case, the people's investment, and trying to be able to say, this is something we can say in confidence, this is going to be a risk because we see it throughout all the forcing ensembles. Here are the ones that are much more uncertain. It may or may not be. And then how do you then try to do future work to improve the knowledge to reduce that uncertainty? So yeah, I think it is an approach. In my case, I've never interacted with those communities. I don't know how to interact, but I think it is something that's important. And we as scientists need to do that with all sorts of spectrum of communities. So the fact that Coast Predict is doing this, I think is great.
Thank you very much, Paul. And now we're moving to our last case study from Samantha Sedlicki. I hope I say that correct, from the University of Connecticut.
You okay?
Yes. You can use your mic.
Okay, perfect. Okay. Okay, perfect. Okay, so good morning. All right, move this a little bit. Is my audio okay then? Okay, perfect. Wonderful. So I'm going to talk to you today about a particular example, following on nicely from everything that's been shown. That is is a case study working with on the east coast of the U.S., the Northwest Atlantic Shelf. And we're working with a particular kind of organism, a very valuable marine resource in the region called the Atlantic sea scallop. And this all came about in part because when I moved from the west coast of the U.S. to the east coast of the U.S., the questions around when should we worry about ocean acidification, because it wasn't as prominent of a concern, kind of emerged. And then within that, kind of questions around how do we long-term plan for marine resources. And so over the past 4 years or so, we've been working on that. And that's the story that I'm choosing to tell you today within the framework of this. And I'll include some technical thoughts on some of the approaches that we took and ways it could be improved as we move forward. So this was a large team effort that includes social scientists. So I'll go to that next slide then. It's a multidisciplinary project. It's co-led with Lisa Colburn, who's a social scientist, and Shannon Masek, who leads as the director of the Milford Lab. She works on scalp physiology. And so there's a large interdisciplinary team here working on this project. And of course, the fishing industry feedback is a core component of the success of this project. So similar to the community feedback that was just mentioned in the Arctic, we also do workshops and incorporate the end users' thoughts in all aspects of our work from the beginning.
So just because this is a kind of a change of topic a little bit, I'll just give a couple background slides about ocean acidification in particular. So CO2 is of course absorbed by the ocean, and then pH is reduced in a predictable way. This is one of the most certain things the IPCC report puts out there, and is something that we understand. So I'll just walk you through that a little bit. Getting my bearings. Okay, so what you can see on this plot here is from observations from Hawaii that have been around for the atmosphere from 1958 through 2024 here. That's from Station Mauna Loa, there in red. And then nearby in Station Aloha, in the 80s, we started collecting water nearby. And so you can see here, this is green. This is the CO2 axis here for both the red and the green. And then the blue here is for the pH axis over here. So what you should take away from this plot is that as CO2 is rising in the atmosphere, the water is absorbing it and for the most part keeping up with that trend. And then at the same time, the ocean pH then declines. And so this is what ocean acidification is. This is just one example from the Pacific Basin right near Hawaii. I'm showing it to you because it is the longest record that we have. But there are records out there from the North Atlantic where we see that things are happening in a similar way. But just like the processes that modify these global rates of change for the physical variables, the biogeochemical ones also similarly are modifying. So all the processes we've heard about, the rivers, the interactions with ice and groundwater, the sediments, like all of that would also impact the local rates of change for ocean acidification variables as well. So this industry is very important to New England, both culturally and economically. So the New England region here is showcased by this map. So we're talking about, down from Virginia. Well, this is the Mid-Atlantic. The New England is kind of from New York further north to Maine. But this whole area collects scallops, right? And so the whole region is important. You can see it's very economically important. It competes with lobster globally for the largest wild-caught managed species in the world. And there's various levels of community dependence of them. So here's an example of that from our social science team showing the community engagement score, so low, medium, and high. But you can see all the different ports up and down the eastern seaboard and how most of them are engaged in some way, right? And of course, that's a scallop, right? So in case you're, and a scallop vessel, yeah. So there you go, yeah. Okay, so sea scallops then are affected by multiple stressors. So they're affected by temperature changes as well as PCO2 changes in the water column, that carbon dioxide in particular. And so we know that they experience mortality when temperatures exceed a certain temperature threshold. So once waters get too hot, they can perish. We also know that ingestion slows as PCO2 increases above particular thresholds, and we know this because of experiments done within the lab, within the lab of Shannon Masick's lab with her postdoc. And so there's a paper there if you're interested more about that. So they did a combined experiment where they did both of these and found that there was less energy available in the combined stress world for growth and reproduction. Which you can also, but each of those would have impacts on the fishery. And then something else that emerged in my knowledge base, but obviously scallop people knew this before, was that the scallops can actually live for a really long time, for up to 20 years. So if we're thinking about managing spatially, for this fishery for a long-lived organism like that, actually the relevant timescale is this climate timescale to sort of be producing information and thinking about decisions for them. So this fishery has already been experiencing some changes. So you can see this is probably really too small for you, but it's 1982 all the way through 2021. So over the past few decades, the fishery's been experiencing a lot of change. So what you can, and there's been a lot of management actions. So that's what's in the red. So we'll start with the biomass first. So this is millions of pounds here. And what you can see then from the black line is the total amount of biomass in the area. And then I've separated it here in terms of the Mid-Atlantic portion, which is in blue, and the New England portion, which is here. So This is further north, this is further south, right? So you kind of see that the biomass where it's being caught is changing and it's moving a bit further north, right? There's been a lot of changes in the management of that. The rotational management program came into effect in around 2004. And that's really credited with a lot of success. So that in the region, they view that that change kind of helped sustain this resource over time. And what they do is they close areas with a lot of fast-growing small scallops in order to protect them and allow them to get to harvest size. And that has been shown to boost the meat yield and yield per recruit and help the fishery out. So given these management changes, emerging multiple stressors, kind of what does a resilient scallop fishery look like? That's kind of what we were asking ourselves. So to answer that question, we did this series of walks around the scallop shell, right? First, we kind of tried to quantify and project the local change, which is a lot of what we're talking about here in this workshop. As part of that, we simulated change in the scallop growth using that lab data that we talked about. We determined the community adaptation options. We examined risk to communities, have an advisory committee that helped us, did a bunch of workshops so individually with fishermen, and then generated management guidance kind of each year and went back and forth with workshops with the fishery to kind of explore these ideas. And so we did workshops all up and down the area from Newport News, Virginia to Barnegat Light, New Jersey, Point Judith, Rhode Island, and New Bedford, Massachusetts, which is the largest port in the region. So 9 total workshops so far, over 88 participants and 62 individual interviews with the fishery. And then on the natural science side of things, we used a historical simulation using the Northwest Atlantic ROMs coupled to cobalt, and I'll talk a little bit more about it in a second. And then we developed a dynamic energy budget model for the sea scallop that we coupled to the projection. And the whole goal here was to try to get maps of projected growth rate and time to harvest in particular. And we're still working on the recruitment changes, but I'm going to show you about the time to harvest ones now. So we used the high resolution regional coupled model under the highest emissions scenario. So that's common theme. We were only able computationally to explore one, and so we chose the one that was the most severe. Here we're using SSP5 8.5, which is a little bit different than the one that was talked about before for RCP because it's from CMIP 6, but it is still the most severe. We used the ROMs coupled to cobalt, like I mentioned before. It has about 7-kilometer resolution. It includes this whole area. And part of that is challenges in keeping the Gulf Stream influences onto the shelf. We can talk more about that offline. And then we used a time-varying delta method to dynamically downscale one of the Earth system models, the GFDL simulation, from daily output using a method that's been described by Mercedes Pozo-Bayul's paper from 2021. So we have a continuous simulation from 1980 through 2100. So how do we trust build and sort of get the community on board with this kind of information? Similar to the prior work, we also relied on observations collected by the fleet. So there's been a series of projects that, in addition to a lot of other observations from the science from the region, one of the ones that we found to be helpful in working with the communities through the workshops was to show them their observations and against what the model was doing. So here are some results there for one particular region. We were limited to just the physical variables at this point, but we are excited to learn about these new opportunities that oxygen has now been given. So beyond temperature and salinity, oxygen is also becoming available. The fleet like has been discussed previously, deploy CTDs. And there's instruments now that just allow it to communicate once it reaches the atmosphere so that the fishermen don't even have to do anything, right, in terms of like relaying the data to kind of minimize the work and impact with them. Okay, the dynamic energy budget model then takes requires forcing for the carbon dioxide level, the food, so this is in terms of phytoplankton and detrital delivery, and then the temperature. And then within that, it calculates energy for, it's like an energy, calculation. So calculates the energy required for the reserves for reproduction and for maintaining the structure of the organism in particular. So here we also compare to observations from the region. And this is work being led by my graduate student, Hallie Berger. And so you can see here she's plotted shell height against time. And that's years here because they live for such a long time. And so you can see the observational comparisons historically compared well. So we were happy with that and went forward doing the projection. And so what you can see now on the left is the age at harvest size in years for the future. So modern age of harvest size, it takes them about 4 years to get to be big enough to be harvested. And so here you can see the spatial variability and so it's kind of basically shrinking, right? That this would take much longer, right? For the area, the deeper it is for them to achieve. And there's some regions that, and some of it grows faster, right? And so some of it, the management time scale will change because some of them, they will reach harvest size faster. So here's the difference between that future state and the historical, kind of highlighting those regions where it takes longer, and some regions where it's going to be shorter. This is all changes spatially things that stress within the communities as well. And so one thing that has been the social science team has been, and Jim Lachance is a social scientist working on the paper about this, showing that New Bedford historically has become basically the primary landing port, even if people are fishing elsewhere. So this kind of changes like a lot of the economic impact to the port itself in terms of its, support of that fishing industry, and also challenges some things. So you can see this here, both the home port and the primary port only, not that they live there. They're just delivering their fish, there. So the takeaway from our research and conversations overall is that basically the OA variables, ocean acidification, affects scallop growth in concert with temperature and food changes, that the current rotational management decisions are informed by observations and models that don't consider this kind of environmental information, including temperature, ocean acidification, and oxygen variability. The industry, through our experience, is eager to help and interested in collecting these observational data themselves. Catch is definitely moving north, and so are landings, despite the home port locale. So it's not, so they're fishing, they're from Virginia, but they're landing in Massachusetts, right? And the fishery is motivated to asking what they can do. Subsurface real-time observations are certainly possible, but they currently don't occupy rotational management areas. And so while we're closing regions of the ocean to help support the baby scallops to grow fast, we don't know exactly what's going on real time within those, but we could, right? And part of the reason for that is that warm events are increasingly common and tend to occur during particular times of the year, which could have potential mortality effects. So what would a resilient scallop fishery look like? We came up with an image like this where, which is a little pixelated in this, but I'm sorry about that. But this is kind of like the lobster cages with the observations on them. That's what one of the fishing groups that is collecting this kind of data. And so as it's near real time, because the sensors are on the cage, and then when they bring it back up, it gets delivered. Of course, the autonomous observations. This is a HabCam, which is something the fisheries is currently using, which takes images to help them with stock assessments, but it's also been equipped with other sensors. So basically, all this ocean information that can then be ingested and and then some pie in the sky stuff about like a benthic rover. I think that would be that was so great. And then bring it together, and bring it into these and compare with these ocean models and be able to deliver it to folks in real time, including on their mobile devices, so that they can be informed. So we kind of explored several specific examples through our last workshop and got industry feedback on them. So one of them was that we could inform these rotational management areas that are currently decided with projections and simulations, right? And then the extent to which they agree and disagree is kind of shown here. They agreed with almost everything. The one they didn't like was altering the seasonality of the fishery to avoid warmer months. They did not want to do that one. But everything else, they agreed. But there was some spatial disagreement. So there was more distrust of the models the further south we were. There was more disagreement about the kind of flexibility needed at sea in Massachusetts because they don't really need it, but the people in Virginia do, right? And then we also discussed like the idea of enhancement in select areas. So we could also, other countries are doing that activity where they're enhancing the natural stock in order to help. And that's something that the fishery actually also had another workshop on afterwards. Including the environmental information into the stock assessment model. And of course, more observations, real-time observations within these management zones in particular. So just to conclude, this process was iterative. It's kind of along the lines, it's co-production of knowledge, right? It was 3 years of workshops, engagements, and large team. We communicated the latest science to industry, and they shared their concerns as part of the workshop, and we very much changed things that we did in response to some of their concerns and took into account their feedback. I'm happy to talk more about those examples with you later. And we used robust data analysis to address their concerns. They're very interested in making this information more available and accessible to them in particular, which is challenging. And they are interested to help making those observations and would love to see more real-time observations within those areas. There was spatial variability in the degree of reliance on scallop for the ports and how that changed over time, and that very much influenced how they responded, and we think, into some of the survey questions. And so these actions kind of may increase the flexibility in the management process, which is important to be, and for the management to be more responsive and adapted in response to emerging events. But in general, I think we have a tremendous capacity to inform, through these climate services, using this kind of co-production approach as a community. And so I look forward to answering any questions if there's time. And if you want to hear more about it, there's the QR code for our project page. Thank you.
Thank you very much. We have time for one quick question, if there is one. If there isn't, okay. One very quick question.
Thank you for a very nice presentation. This linkage between the end users and the scientists is very important. And my question is, what mechanisms do you use to convey the information to them in a way that they can grasp the meaning and the understandings quickly?
Thank you so much for that question, because I forgot to mention something, which is that we could not have done this without one of the organizations that's on here, which is the Commercial Fisheries Research Foundation. They are co-PIs and help plan the workshops. And, they are what I call a boundary spanning organization, where they have they've been working with the fishery. Some of them were out there and were fishermen before this. They've been working with them for a long time. That long time relationship exists, right? And they also helped us we did pilot workshops with them before we went and did the real workshops to help us de-jargonize, because jargon is a real serious issue in kind of science communication, and like fine tuning our messages, and making sure they were short, and not like over, us having like these huge long seminars. And so we worked with them, and benefited enormously from their relationship with the end users, in addition to doing these pilot workshops before we actually went on the main workshop. And I think both of those things helped out a lot.
We go to the coffee break. We have an announcement to make.
I just wanted to let you know, so we're being joined online by a lot of people. And I just wanted to let you know some of the countries that are represented online today. So we have people from Ghana, Colombia, Sudan, Tasmania, Australia, Yemen, Brazil, Spain, the Philippines, Nigeria, and Dubai. They're not all of them. I just grabbed a few just to give you a flavor of where people are joining us from. And to the people online, thanks so much, because I know you're coming from different time zones. We weren't able to get to some of the questions that came through online, but I'll confirm with Anna that we'll be able to share the presentations. Yeah.
Some of the questions that they were put online, probably they can be addressed in the breakout session. So maybe we can revisit them during the breakout session. So for the online people, the breakout and for the people in person, we are late, so we're gonna start the breakout session at 11:40 instead of 11:30. And for the online people, you should receive your assignment themes. If you haven't provided any feedback, you may not have been assigned. Please choose a theme and attend. And if you see that there are 40 people, just go to another room. I mean, you can figure it out. For the in-person people, they should be printed out of where you have been assigned if you have provided information. Even if you haven't been assigned, please choose one session to attend. And now we can have a break. Thank you very much.